Hello and welcome again to another key tutorial in the series on MPLS. Today I want to talk about quality of service. First of all, why we need it, and then we'll dig in to look at the bits and bytes of how it's implemented in general terms, and then how we map it into an MPLS network. Let's start by considering our road networks. Isn't it great when you're driving on an open road with no other traffic getting in the way and you can travel at whatever speed you want to? Unfortunately, this scenario is rare, especially in busy towns and cities. It's more common to find yourself frustratingly behind a line of cars and trucks and you're forced to slow down. If only there was a way to get ahead. Perhaps if you put a blue light on the roof of your car. Consider this situation. The road narrows from 3 lanes to 1. As you approach the narrow part, you might get held up for a while, especially if there are emergency vehicles around. You're stopped as the higher priority vehicle is allowed to go through ahead of you. In a communications network, the higher priority traffic is often the real-time services like voice or video, and the lower priority traffic is the services that are not real-time like web browsing. So, in the world of communications, how do we label one packet as high priority and another as lower priority? Well, let's get stuck straight into looking at an IP packet header. As you can see, in an IP version 4 header, we have 6 bits available to us, which are used by a hierarchical system called differentiated services, or diffserv. 6 bits are used to hold a number called a diffserv code point, which is the priority value for IP, something that indicates the type of service being carried in that packet and how it should be handled. At each point of potential congestion in the network, such as a router, the diffserv code point of all the incoming packets are checked. In the buffer, the order of the packets for transmission is rearranged according to the relative priorities. Take a look at this animation and keep an eye on the packet with the dark orange code point. At the first node, it arrives with other packets and all the code points are checked, and our packet is found to have the highest priority, so it's transmitted first. At the next hop, the process is repeated. Our packet is once again found to have the highest priority and again is transmitted first. The priority decisions are made node by node or hop by hop, and for this reason this type of prioritization is called per hop behavior, or PHB. A word about the various codes available in diffserv. Practically speaking, the highest priority code available is decimal 46, which is called expedited forwarding. The lowest priority code is 0, and this is called default forwarding. In between are groups of codes called forwarding classes. So, a packet assigned an expedited forwarding code point will be prioritized for transmission ahead of packets assigned any of the other code points. And one more thing to mention. Included in the assured forwarding class code point is an extra piece of information called drop precedence. Now, if the router uses traffic policing and decides to drop certain packets rather than transmit them, the code point within the forwarding class indicates which code point is more and less likely to be dropped. Counterintuitively, the higher the code point in a class, the more likely it is to be dropped. So turning back to MPLS, You remember that MPLS transmission is based on the simple reading of a label in the shim header at each LSR in the network. So, if we are going to use the diffserv information for intelligent handling of packet types, where in the shim header can we carry the diffserv code points? The answer is in a 3-bit area called the traffic class field, using what was once known as the experimental bits. So, you may ask, how can 6 bits of diffserv code point be carried in just 3 bits? And the answer is that we must be selective about how many diffserv code points we use. If we recognize that 3 bits of information equates to 8 options, so in an MPLS network, only 8 diffserv code points can be used, and the mapping of code points to traffic class is explicitly coded in configuration, and it's configured identically in all LSRs across the full path. Notice potentially we are carrying both priority and drop precedence information in our 3 bits. This is one of 2 methods of implementing quality of service in MPLS, and by far the most common. It's called explicitly TC encoded LSP, or ELSP for short. And we can use the same method if there are VLAN tags present. Here, the priority information is carried in a 3-bit field called the priority code point, or PCP. So, this time, rather than using the diffserv code point, the PCP value in the VLAN tag is used and mapped to the MPLS traffic class. The mapping might be 1-to-1, or as the diagram here shows, 2 or more PCPs might be mapped to a single traffic class. As an alternative to ELSP, there is an alternative method called LLSP, label only inferred LSPs. Here, the priority part of every IP scheduling class, or PSC, that's in use is first mapped to a special MPLS PSC. This is then assigned to an LSP. The PSC is said to be inferred from the LSP or the label. Now, the diagram only shows 3 LSPs, but of course many more could be used. And the drop precedence part of the PSC, where relevant, is mapped to the traffic class bits. And the same principle applies for LLSP if VLAN tags are present. First, the PSP is mapped to an MPLS PSC, and secondly, the PSC is assigned to an LSP. It should be noted that LLSP is a far more complex system than ELSP. There's much more configuration required, and for this reason, it's recommended that ELSP should be used where at all possible. So returning to ELSP, let's now look at how each LSR in the network transfers the priority information, or per hop behavior, at each stage. First, the ingress LER. The diffserv code point, or VLAN tag PCP, provide the input for mapping to the so-called incoming PHB. Configured mapping called traffic conditioning may be used to modify the outgoing PHB. Otherwise, the outgoing PHB will simply be identical to the incoming. And finally, the outgoing PHB is encapsulated by mapping into the traffic class of the shim header, and the packet is transmitted towards a transit LSR. Next, at the transit LSR, the PHB is de-encapsulated from the traffic class to provide the incoming PHB. And just like in the ingress LER, there is optional traffic conditioning where the PHB could be manually mapped to a modified outgoing PHB or kept the same. And finally, the outgoing PHB is encapsulated into the traffic class of the shim header again. Finally, at the egress LER, the PHB is de-encapsulated from the traffic class to provide the incoming PHB. And here there can also be optional traffic conditioning, as before. The last section is to encode the PSC into the customer diff serve code point, or PCP. But how the egress LER operates at this final stage is determined by one of three final stage models, which we will look at now to finish. The first and most common model is called the pipe model. Two criteria are considered: forwarding and customer PSC. In the pipe model, the forwarding of packets is according to the MPLS PSC held in the traffic class, and the packet continues its journey to the customer edge with the original customer PSC, for example the diffserv code point in the IP header. The second model is called the short pipe model. Here the difference is that the forwarding of packets in the egress LER is according to the customer PSC. But as with the pipe model, the packet exits the MPLS domain with its original customer PSC. And lastly, the third model. This is called the uniform model. Like the pipe model, the forwarding of packets is according to the MPLS PSC. But, unlike both pipe models, the original customer PSC is discarded and replaced with a copy of the MPLS PSC for its onward journey to the customer edge. And that's the basics of how quality of service is handled through an MPLS network. Thanks for sticking with me. KeyMile is a leading worldwide manufacturer of carrier-class transport network systems. KeyMile is ready to support your MPLS requirements and more, with rugged, reliable, secure, feature-rich platforms manufactured in Europe that will meet the needs of your mission-critical networks today and tomorrow. KeyMile, because connectivity matters. Thank you for watching this key tutorial.